Hello and welcome. In the following video, I'm going to cover the broad topic of topological sorting as applied to algorithm problems. In particular, one of the canonical problems that you can find on the Leetcode platform, which is called the course schedule problem. You should consider using topological sorting when the problem is asking you to find a potential order of events, processes, tasks, courses, etc. And set objects and their relationships can be represented by a directed acyclic graph. It must be noted that for this type of graph, if it contains cycles, for this problem it simply won't be possible to complete all the courses. Outlined right here is Kahn's algorithm for topological sorting, which we're going to use to solve the course schedule problem. The first step, of course, is to build a graph. We're going to use the input that is given as an array of tuples or two-element arrays, and each one of them is read right or left. For example, tree 1 means that course number 1, civil law, has to be taken before course number 3, human rights. Therefore, in the graph, we're going to draw an edge from course number 1, civil law, to course number 3, human rights. For the current edge that was drawn, we're also going to increment the dependent vertex in degree value by 1. The in degree value of a course represents how many requisite courses the student must complete before being able to take it. So in the case of course number 3, human right, you can see that there are 2 courses that need to be completed before you're able to take it. Once the graph has been assembled, we'll use a queue data structure to push the courses with an in degree value of 0 into it. These are the courses that have no initial requisites or the ones that are ready to be taken. We're going to use a standard BFS to discover which courses can be taken next. To do that, we're going to pick each course in the queue that holds the ones that are ready and move them to our result set. For every neighbor node or course removed from the queue, we're going to explore its neighbors and reduce their in degree value. If a neighbor course's in degree value reaches 0, then it means that course is ready to be taken. Therefore, we push it into the queue. Let's try run the BFS step to see this algorithm in action. While our queue is not empty, we can see that it's not empty. We take out a node from the queue and add it to our result set. For every neighbor node, decrease its in degree value by 1. Check if neighbor's in degree value has reached 0. It's false. Let's explore the next neighbor. Decrease its in degree value by 1. Check if neighbor's in degree value has reached 0. No, it's not. Let's move to the next neighbor. We're done exploring neighbor nodes, so let's move to the main while loop. Is the queue empty? No, it's not empty. Let's take out the next course that is ready to be taken from the queue and add it to our result set. Let's explore the course's neighbors. In this case, there's only one neighbor. Decrease its in degree value by 1. Check if neighbor's in degree value has reached 0. That's true. Then it means our course is ready to be taken. Let's move it into our queue. Let's go back to the main while loop and check if the queue is empty. It's not empty. Let's take out the course that is ready to be taken out of the queue and add it to the end of our result set. Let's explore each of the neighbor courses. Let's start with course number 4, state law. Decrease its in degree value by 1. Check if this course's in degree value is 0. That's right. Then it means this course has no more dependencies. We can push it into the queue. Let's explore the next neighboring course, business ethics. Decrement the course's in degree value by 1. Check if this course's in degree value has reached 0. That's right. Then it means this course has no more dependencies. We can push it into the queue. With no more neighbors to explore, then we go to our main while loop and check if the queue is empty. It's not empty. Let's take out the next course that it's ready to be taken and push it to the end of our result set. Course number 4, state law, has no neighbors to explore, so we go back to our main while loop. Because the queue is not empty, we can go ahead and take the next course from the queue and add it to the end of our result set. Course number 5 has no neighbors to explore. Therefore, we go to our main while loop and check if the queue is empty. And this time the queue is empty. Because the queue is empty, we can finally break out of our main while loop, which means we're done with the BFS step and we can safely return our final result set topologically sorted. So here's Leetcode 210 course schedule 2. It's the same problem that we reviewed in the overview of this video. And as you can see, its entry, it's an array of the prerequisites. Prerequisite entry is defined as a course and its corresponding dependency. We're going to use these values of the input to assemble our graph. Okay, so the first step, therefore, is to have the data structures defined to assemble the graph and to store the in-degree values. Here, each entry of the graph will contain each individual course and its dependencies, and this linear vector will contain the count for the in-degree value of each individual course. The next step is to actually populate the graph in the graph data structure and degree data structure that we just created. To do that, we're going to traverse the prerequisites here and populate each one of these tuples into the graph. As explained before, we're going to draw an edge from this course into this dependent course. So how does it look like? Once our graph has been assembled, the next step is to define the queue that we're going to use for our BFS step and a vector to store the results of the topological sorting. And that looks like this. Next, we need to figure out which courses we can immediately push into the queue. Those are the ones that have an in-degree value of 0. In order to do that, we're going to traverse the in-degree array and discover which ones have a value of 0. It looks like this. Let's write the VFS step that follows Kahn's algorithm. So how it works is, while the queue contains courses that are ready to be taken, we're going to pull each individual course out of the queue and explore its neighboring courses. For each of the neighboring courses, as explained in the overview of this video, we're going to decrease its in-degree value. And once that in-degree value reaches 0, it means that we're able to push it into the queue because it's going to be a course that is also ready to be taken. All right, let's begin with the main while loop that checks if there are still courses to process in the queue. We're going to pull each of the courses that are ready to be taken out of the queue and push them to the end of our result set. For the current course that was removed from the queue, let's explore its neighbors. Finally, for each neighbor course, we're going to decrease its in-degree value, and if this in-degree value reaches 0, as explained in the overview of the video, it means that the course is ready to be taken, and therefore we're going to push it into the queue. Alright, that was it for the BFS portion of this algorithm, and the only thing that remains is to return the result, and we have to make a little check to see if the number of courses in the result is the same size as the courses that were passed here as a parameter n in the main function. Okay, that's all for the coding part. Let's see if it works. Awesome, and it does. In part 2 of this series, I'm going to show you how this template logic can be applied to slightly harder problems. For now, I really hope you liked the video, and thank you very much for watching. See you next time.